This video is for lesson 5, derivative shortcuts and examples, part 1. All right, let's get started here. In a previous video, we saw the limit definition of derivative. It's essentially the limit of a slope formula from algebra as the horizontal distance between the 2 points that you're plugging in the slope formula gets closer to 0. The points get closer to each other. You should definitely know this. However, it becomes cumbersome to try and use this every single time you want to find the derivative of a function. Luckily for us, we know that there are all sorts of shortcuts that can help us figure out derivatives very quickly. So most of this video is just going through some of those shortcuts. Real quickly, before I jump into that, just a couple quick reminders here. Derivative definitions get kind of funky at endpoints. You are allowed to consider differentiability at an endpoint. You would just use a one-sided version of the limit above. If the one-sided limits are not equal for points that are not an endpoint, meaning they are within an interval, then we say the function is not differentiable. Okay. Anyway, moving on to shortcuts. Here I have the first 3 of many important rules. There's a product rule, which we use if we're trying to find the derivative of a function being multiplied by another function. Similarly, we've got a quotient rule. You're trying to find the derivative of a function divided by another function. You might have seen these written slightly different ways when you learned them last year. If you memorized them a slightly different way, by all means, use the way that you know. As long as you're getting the right answers, it's totally fine with me. But essentially, the product rule, we take derivative of one of the components of our product times the other component unmodified. And then we add that to basically flipping the roles. We take the derivative of the other part times the first part unmodified. Okay. I'll let you take a look at the other rules on your own. Chain rule, this is when we have a derivative of a function essentially plugged into another function. The derivative of f of g of x, more commonly written using this parentheses notation. Actually, it's not even totally written here, is it? F of g of x is the more conventional way to write that, but the derivative, well, we take that outside derivative, f prime, with the same interior function still plugged in, multiplied by the derivative of that interior function. Here's yet another way to write that. So spend as much time as you need to make sure you have these memorized. We will use them throughout the year. Moving down to the next page, we see a whole bunch of other ones. Probably the most common one, the power rule. For polynomial terms, derivative of x to the n becomes n times x to the n minus 1. Derivatives of a constant, of course, are 0. I'm not going to necessarily read through every single line of this for the rest of them. But these are all formulas that you have seen before, and you want to relearn them ASAP. And of course, ask me if you have any questions about anything that you're seeing in here. Okay. The rest of this lesson just contains a variety of examples where we're using a lot of these different rules. And I'm also trying to fold in some problems that tend to show up on AP style questions, whether it's free response or multiple choice. This first one, for example, we see a reference to a function f, a function d. We don't know the actual equations for those functions. We do happen to know a couple values of those functions at certain x's. We know a couple values of their derivatives. Based off of just that, we're going to try and calculate some derivatives mentioned here. The first being find f of g of x. That looks like a chain rule setup, specifically when x equals 1. When I work through problems like this, I don't really concern myself with the specific x value mentioned, at least not initially. What I like to do first is just make sure I have a correct general formula written down. So if I were to take the derivative with respect to x of f of g of x, I know from chain rule that we're going to use f prime of g of x times g prime of x. So I get that down on the page first. Once I have it there, then I just replace all the x's with a specific x value, in this case being 1. So now I know I need to look for f prime of g of 1 times g prime of 1. And now I can start pulling numbers from the table. G of 1 in the interior of this first component of the product, we know is 2. So this first whole part becomes f prime of 2. And thankfully, we know f prime of 2 becomes a 6. Meanwhile, g prime of 1 is -1. So my final result is basically 6 times -1. Okay. Moving on to the next one, square root of g of x. If we're going to take a derivative, the better way to write this is probably, as I've done here, g of x to the 1/2, because now it aligns with that power rule shortcut. So I'm interested in taking the derivative with respect to x of g to the 1/2. And of course, the power rule tells us to go with 1/2 times g to the -1/2. But then I'm using chain rule again, because this thing right here that's being raised to the 1/2 is not just an x by itself. It's an entire function being plugged into the square root function. So whatever I started with over here on the right, I have to then multiply by derivative of that inside function. Again, I'll deal with all of that first before worrying about the x value of interest. But now that I have it, I will start plugging in x equals 2. So we'll need g of 2 and then g prime of 2 in a couple different places. I've made this appropriate substitutions, and from there it's just pre-algebra work to make sure you simplify that correctly. Part C, careful here. This is not g of x plus f of x. If you look closely, it's g of the quantity x plus f of x. Okay. So to take the derivative of that, I'm going to go with g prime of that entire inside portion, x plus f of x, multiplied by the derivative of x plus f of x. And of course, the derivative of the x is just 1. The derivative of f of x, we simply say f prime for now. I've worked it out in the general sense, and now we go through and replace all the x's with x equals 1 again. So we've got g prime of the quantity 1 plus f of 1 multiplied by the quantity 1 plus -4. F of 1 we're grabbing from the table, adding 1 to it. We eventually get g prime of 2 times -3, and from there we can get to an answer. Part D, I'm seeing product here, so product rule, but I'm also seeing chain rule. Yes, it's possible to combine various derivative rules all into one expression. So we want the derivative with respect to x of g of x squared times f of x. Be really careful writing out your work here. It's hard to get this down in your head. But yeah, from the first part, I take the derivative of that first component, it becomes 2 times g of x to the first multiplied by the derivative of g of x. But then I also have to multiply by the other portion of the product unmodified. So just regular f of x. And a big plus sign. Now we're moving into the second half of product rule, in which case I can take the first component unmodified times the derivative of that second component. It's kind of a lot going on there, but if you work it out in general first, now we can just plug in this case, the number 2 to everywhere I saw an x. And again, you're then pulling values from our table, and we can get to a numerical answer. All right. Second derivatives and beyond. We've talked in previous videos about how the derivative in and of itself is a function, which of course means then perhaps you could then differentiate that, get to a second derivative or beyond. Here's some of the common notations for that. Why would we be interested in doing that? Well, in certain contexts, rate of change is useful information. The most commonly used one for us right now is acceleration being the second derivative of position, or you could alternatively say acceleration is the derivative of velocity. And we could also keep going with the third, fourth, fifth derivative. I think the third derivative of position is called jerk, interestingly. We don't really use that terminology in this course, so you don't need to know that. All right, example 5.2. And really from here down to the end, just again, a few more examples where we're using first, maybe second derivatives, things like that. So we start with an equation for position of Thor on a certain axis. We're asked to find equation for velocity. So I'm just applying my power rule shortcuts to each of the terms of this original polynomial. Now, something we want to get in the habit of, if this were a free response question, you might actually get penalized if you don't label your work very clearly. Okay, so I wouldn't want to just write down 3t squared minus 30t plus 48. I want to make sure I'm labeling it as a velocity. I'll call it v of t equals that result. Okay. Part B, find an equation for acceleration. Well, I'm simply going to take the derivative of the previous derivative. I'm going to label it nice and clearly. We get 6t minus 30. Next, we want to find the acceleration at specific times when the velocity is 0. So that means I want my v equation to be equal to 0. I want this quantity right here to equal 0. So I'm setting it equal to 0. You'll notice I did a little bit of factoring first just to make it easier to solve, but it really is an algebra problem at that point. We get two values of t, but I'm not done because I want to find the acceleration at those values of t. So now I'm plugging each of these results into the acceleration equation we found a moment ago to get my final answers. And of course, I'm going to put units on there if they apply. Position was meters. Velocity, therefore, is meters per minute. Acceleration is meters per minute, or you are allowed to say meters per minute squared is acceptable. At what times is the velocity negative 27 meters per minute? Well, that's very similar to the previous part. It's just now I want to set my velocity equal to negative 27. Luckily for us, you move some things around. It's an algebra problem again. This one was easy to factor. We end up with a single time answer. All right, moving on to 5.3. You will see geometry formulas come up periodically throughout this course, and we're dealing with changing sizes of geometric shapes, sometimes 2 dimensions, sometimes 3 dimensions. So rates of change and derivatives are useful here. I will say the trend recently is when geometry shows up on the AP test, they do usually give you relevant formulas. So I can somewhat confidently say you don't necessarily have to memorize a bunch of geometry formulas right now, but all the same, it is good to know them. Perhaps you remember this one. Area of an equilateral triangle. I'm not looking for a 1/2 base times height. I'm actually looking for this guy right here. Maybe you remember it. Side squared root 3/4. That works specifically if you know all 3 sides of your triangle are equal. We want to find the rate of change of this area equation with respect to s, which is side length. So for one thing, you're not going to call the derivative f prime. There is no f referenced at all in this problem. I guess you could get away with calling it a prime, but the better notation is one that clearly communicates what we're differentiating with respect to. So I prefer rate of change of area with respect to side length. And I'm just applying a shortcut formula to get there. Now that I've got it, I can use it to find the actual rate of change of the area of this triangle at specific moments, like the moment when side length happened to be 2 centimeters. Okay, I neglected to put units here, but it does ask about it in the next part. We want the units to be the units of area divided by units of side length to match the a over s that we're seeing in our notation. So centimeters squared per centimeter is the way you would read this. I would advise you not to try and simplify this to just say centimeters as if you're like canceling out a copy of the unit. That doesn't really make sense contextually. You want to leave it as centimeters squared per centimeter. 5.4, see piecewise functions coming back. We want to find the derivative. And unfortunately, it's right at the location where the pieces split. Now, you could certainly graph this if you want. We are interested to know if these pieces actually connect to each other, because remember, differentiability requires continuity, meaning if I were to plug a -1 into each of these pieces and I don't get the same answer, well, this piecewise function isn't even continuous. It doesn't have a derivative. It would be pointless to do any further analysis. In this case, however, if you plug a -1 into both, you do get the same result both times, which means this function is continuous. Now, that doesn't guarantee that we have a derivative, but it's possible. So we do need to continue looking. And the way to do that is to simply take each piece of the g of x, find its derivative. So from the left, okay, from the left, the derivative is -2 over x to the third. And find the g prime coming in from the right side. The formulas don't match each other, but that's okay. We just need to be able to plug in -1 again to both pieces. If we get the same result, we're good to go. So plugging in -1, we don't get the same result both times. So even though we were continuous at -1, we do not have differentiability at -1. So I guess you could say g prime does not exist. .5, we have actually seen an example similar to this, I believe in a previous video. We're asked to, well, actually, we're not asked to necessarily, oh yeah, we are asked to calculate the limit. Looks kind of funky. If you try to plug in a 0, you get stuck, but that's not the approach we're actually supposed to take. We're supposed to recognize this as a limit definition of a derivative. And of course, the giveaways are an h going to 0, h in the denominator, a difference of 2 terms on the top, okay? So what we suspect is that this first term on the top is trying to tell us an f of x plus h. I see a 3 plus h, so it seems that the x value of interest is 3. So not only is this representative of some kind of derivative, it's specifically a derivative of a function when x equals 3. That's good to know. The only other thing we really need to know then is what is the actual function? Well, to learn that, we just need to figure out what is it that we're doing to this x plus h. And it appears that we are taking our x plus h and raising it to the 4th power and then multiplying by 2. So even though we're interested in x equals 3, it looks like in general, the function being applied here is 2 times x values to the 4th. Now, seeing that this entire expression represents a derivative of our function, we would immediately take our function and find its derivative, but we're going to use a quick shortcut. There's nothing in the directions here that says you have to use the full limit evaluation technique, so we're going to get away with the shortcut here. And then, of course, keeping in mind that we're interested in what happens when x equals 3, we just plug in a 3 to this right here, and voila, we get an answer of 216. Okay, last example for today's video. Here we have a graph of 2 functions that appear to have corners, look very much like possibly absolute value graphs or something of that nature. Although I don't appear to see symmetry in one of them, so maybe it's not exactly an absolute value, but it doesn't matter. We're referencing a function called capital G, which is set equal to 3 times some other function called f, and that's one of our graph functions, minus little g, which is the other function from our graph. Based off of just the graph, not knowing anything further about the actual formulas for these equations, we're supposed to find g prime of 3. This is another scenario where I'm going to worry about just the general derivative before I worry about plugging in a 3. So I'm going to say g prime, or g prime of x, which is what I would get if I differentiate the left side of this initial equation, would have to be equal to the derivative of the right side. So 3 times f prime minus little g prime. Now that I have it there, I'm going to plug in 3's everywhere. I use kind of a shorthand notation where I just call these functions f and g, but really it's little f of x and g of x. So I can certainly replace my f prime with f prime of 3, g prime of 3 if I'm going to plug in a 3. Okay. And f prime of 3, g prime of 3, those refer to derivatives, or in a graph, they refer to slopes. So this is telling me I need to figure out what is the slope of the f graph at 3. And the whole first piece of the f graph, which is including x equals 3, has a constant slope I could easily count as down 3 over 1. So this first term becomes 3 times -3. Likewise, g prime of 3, okay, if I look at the g graph, that's first piece, which includes where x equals 3, its slope appears to be 1. So I end up subtracting 1. And yes, I am able to get an answer here, even though I never knew the equation for g prime. I never had a graph of g prime, big G prime. Still able to evaluate that. All right, hope you enjoyed the video. Let me know if you have any questions, and thanks for watching.